Section 12.3, double integrals in polar coordinates, video 4. In the previous video, we set up a double integral in, it was already set up in rectangular coordinates, and we were given this polar rectangle over which to integrate. And so we converted it to a double integral in polar coordinates by replacing x with r cosine theta and y with r sine theta. And this is the part students tend to forget, when you set up the differential for dA in polar coordinates, it is r dr d theta. A lot of students forget that extra r. All right, so let's just integrate this. If we're going to integrate it first with respect to r, then we should probably go ahead and distribute this r. In fact, let's focus on the inner integral, the one integrating with respect to r. And then when we finish that, we'll just import it back into the double integral and take it from there. So if we want to integrate from 1 to 2 and go ahead and distribute the r, 3r squared cosine theta plus 4r cubed sine squared theta dr. In this case, as an iterated integral, we're pretending that the thetas are constant, so they just sit there and do nothing while we integrate the r's. So for all intents and purposes, this first term, the constant is 3 cosine theta and the variable is r squared. And so if we integrate that, we will get r cubed cosine theta. And then for the second term, same thing. The 4 sine squared theta is essentially constant relative to r, so we're just integrating the r cubed. And if we integrate the r cubed, we're going to end up getting r to the 4th sine squared theta, and we are evaluating this from r equals 1 to r equals 2. So if we substitute 2, we will get 8 cosine theta plus 16 sine squared theta minus, if we substitute r equals 1, we get cosine theta plus sine squared theta. And so we have 7 cosine theta plus 15 sine squared theta. Now be careful, that's not the end, and it's not time to substitute 0 and pi for thetas, because we have not integrated with respect to theta yet. That's just the value of the first of the 2 iterated integrals, the inner integral, if you will. And so let's import this back into the double integral, which is no longer a double integral. And now we just have to integrate from 0 to pi. The expression 7 cosine theta plus 15 sine squared theta d theta. I would actually treat this as 2 separate integrals for the 2 terms in the integrand, because the first one's straightforward and the second one's not. So let's just deal with the first integral first. The integral from 0 to pi of 7 cosine theta d theta. The antiderivative of cosine is sine, so 7 sine theta from 0 to pi. So 7 sine of pi minus 7 sine is 0. Well, both of those are equal to 0. Well, that was uneventful. All right, so that part finishes. Let's see. So now we just have to integrate the second part. So let's get rid of this and get ready to deal with the integral of 15 sine squared theta d theta. This one's going to take a little bit more work. Integral 0 to pi of 15 sine squared theta d theta. By now, you should be familiar with how to attack the integral of sine squared to cosine squared. For both of those, you would have to use what's called a power reducing formula. The power reducing formula does exactly what its name implies. It reduces the power, but the trade-off is it doubles the argument of the trig function, so this will become a 2 theta. Now, I'll be the first to admit that I don't have the power reducing formulas memorized, but I do know where they come from, and I can rederive them when I need to. It would probably be quicker to memorize that, but I would rather understand than memorize personally. For the power reducing formulas, you have to go back to double angle formulas. For example, and both of the power reducing formulas are based off of double angle formulas for cosine of 2 theta. Because the double angle formula cosine of 2 theta comes in 3 flavors. One involves sines and cosines, one involves sines, one involves cosines. Since I'm dealing with sine squared, I'm going to use the double angle formula 1 minus 2 sine squared theta. That is one of the double angle formulas for cosine of 2 theta. Now, how can I use this to do a power reducing formula? If I solve this for sine squared, I would probably, there's no probably to it, I would move the negative 2 sine squared to the right and the cosine 2 theta to the left, because when I'm solving for sine squared, at some point I need to divide by the number in front, and I would rather it be positive. So let's move the 2 sine squared to the right, leave the 1, and move the cosine 2 theta to the other right. Move the 2 sine squared theta to the left, it'll become positive. Move the cosine 2 theta to the right, it will become negative, and then I can just divide both sides by 2. And I'm literally going to divide each of these by 2. So 1/2 minus 1/2 cosine 2 theta. And that is your power reducing formula for sine squared theta. It'll give us the integrand in terms of cosine of 2 theta, which I can integrate a little more easily. I'll have to do a quick substitution for the 2 theta. The power reducing formula for cosine squared would look almost the same. The only difference is it would be a plus. Yes, it would be a plus. Just for some reason that made me freeze for a moment. So anyway, this is our power reducing formula that we're going to use. And so that would transform the integrand to 15 times 1/2 minus 1/2 cosine of 2 theta d theta. And now we just integrate. We just integrate, that's all. It's just a calculus 1 problem. I'm going to do myself a favor. I'm going to factor out not only the 15 but the 1/2. So 15 halves integral from 0 to pi of 1 minus cosine 2 theta d theta. And now I can just integrate each of these separately with respect to theta. The integral of 1 with respect to theta is theta. We could do a real quick u substitution here if you really needed to. You would say u equals 2 theta, so du would equal 2 d theta, which means you would need a 2 in front of the d theta, but you would have to balance it with a 1/2. So we will pick up a 1/2 upon integrating. The integral of cosine of sine, or antiderivative of sine, of cosine of sine. If you're not sure about the substitution move, just quickly redifferentiate. Derivative of sine is cosine. Chain rule would pick up an extra 2, which would cancel the 1/2. This is getting evaluated from 0 to pi. So we will have 15 halves times, if we insert pi, pi minus 1/2 sine of 2 pi. And then insert 0, 15 halves, 0 minus 1/2 sine of 2 times 0, which is 0. That's gone. Sine of 0 is 0. Sine of 2 pi is also 0. So everything disappears except the 15 halves times pi. So we'll get 15 pi over 2, or 15 halves times pi. Hey, which is exactly what they got on page 711. Not too bad for doing it off the top of my head. So as you can tell, sometimes the hardest part isn't getting the integral ready, it's actually doing it. Sometimes. Personally, I think the only reason this integral was even slightly challenging was the presence of the sine squared. But again, by now you should know that when you integrate a sine squared or a cosine squared, you have to use a power reducing formula, which is just a tricked out version of a cosine double angle formula, to lower the power to 1, and as a consequent, double the argument of the trig function, which just sets up a small substitution issue.